Why, hello everybody. How is everyone doing today? All right, good. Hey, first off, I'd appreciate if you would pray for me. I'm in West Virginia. I had to leave unexpectedly. My sister-in-law passed away. She had a heart attack very early Friday morning. So I'm in West Virginia for a few days with my brother-in-law. So just pray for me and my family as we go through this very difficult time. So, hey, all right, we've finished up solids and liquids, and now we're going to be starting the chapter on gases, okay? So, here's just a few things that we're going to be talking about: the atmosphere, atmospheric pressure, barometers, okay? Boyle's law, buoyancy of air, Bernoulli's principle, plasma. We're only going to touch on some of this today. We'll be getting through this over the next week or week and a half. So first of all, I'm going to make myself a little smaller here. There we go. Okay. So first of all, think of the atmosphere as just a massive ocean of air, and think of above you all these air molecules which are stacked on top of one another, and so the more air molecules that are stacked on top of you, the much heavier it is. So the higher you go in the atmosphere, the lighter it becomes. So Otto van Gurik, he demonstrated the effect of air pressure by using what's called the Magdeburg hemispheres. And I think we've talked about this a little bit previously, but the Magdeburg hemispheres, you can see here, it's these metal spheres which are joined together, and the air is sucked out of it. And then he hooked up a team of horses on either side and that were pulling these things apart, and demonstrated that air pressure is so great that even a team of horses couldn't separate these things. Okay, so that's the Magdeburg hemispheres that we're talking about there. So when we think about the atmosphere, we're talking about a compromise between kinetic energy of the individual particles and gravity pulling these particles towards Earth. Remember, everything is falling towards Earth, so these individual particles that are all around us are falling towards Earth at 9.8 meters per second squared. That's right. But they're also at the same time moving. Now, the sun is causing all of these particles to have kinetic energy. So if the sun were to go away, that's right, there would be no more kinetic energy in these particles. These particles would no longer have energy. So these particles would no longer be moving up and moving back down. So we have these things called convection currents. So as the air gets hotter, warmer, it becomes less dense and it rises. And as it rises, it's now pushing down the cooler, more dense air. And we have these convection currents flowing in the air. So if the sun were to go away, it would be bad because suddenly we wouldn't have these convection currents. We wouldn't have this uniform heating of the Earth because, we do have some daily variation in temperatures of the air, but mostly because of our atmosphere, the temperature stays relatively constant. We don't have daily shifts of 100 degrees Celsius or more like there are on some other planets where there's a thinner or no atmosphere. Atmospheric pressure, as I said before, this is caused by the weight of air. So if we stacked up all these air molecules above you, then this would become very, very heavy. So the atmospheric pressure changes from one spot to another, and depending on where you are. So higher in elevation, less air above you, it's going to be less air pressure. And it's not necessarily uniform everywhere. So it's this atmospheric pressure that we can use to predict what the weather is going to be like in different spots, because air moves from areas of high pressure to areas of low pressure. So areas of high pressure are sunny, areas of low pressure are often rainy. So we can look at the the atmospheric pressure, and we can decide what's the weather going to be like tomorrow, the next day, because of the pressure that's in that area. So the pressure exerted against bodies immersed in the atmosphere results from the weight of air pressing above them. At sea level, we're talking about 101 kilopascals. So the weight of air pressing down on 1 meter squared at sea level is about 100,000 newtons. So atmospheric pressure is about 10 to the 5th Newton meter squared. Okay, so again, at sea level, the weight of air pressing down on 1 meter squared is 100,000 newtons. That's a lot. Now, maybe I guess I should say it, but pressure at the bottom of a column of air reaching to the top of the atmosphere is the same as the pressure at the bottom of a column of air 10.3 meters high. So the highest the atmosphere can push water up into a vacuum, 10.3 meters. Doesn't matter, 10.3 meters. That's as high as water can force, or I'm sorry, that's as high as the atmosphere can push water back up on something. So mechanical pumps. So the picture here of these people using this hand pump, I don't know if anybody's ever used one of those things. The highest this pump or the deepest this pump could go, this well could go, would be 10.3 meters. That's it. 30 feet. That's it. Can't go any deeper than that. All right, so I've already given you the way to answer here. So if you had a straw, what's the longest the straw could possibly be and that you could drink through? Yeah, 10.3 meters. That's it. It doesn't really matter. Anything else, doesn't matter how big your lungs are, how strong you are. 10.3 meters is as long as the straw could be for the atmosphere to push the water up through. Okay, that's where we're going to end for today. Thanks for watching my video. Thanks for praying for me. Don't forget to do the daily attendance forum. All right, so I guess that's all we have for now. See ya.